everyone, welcome to Brainstorm. This is our Level 2 Algebra walkthrough. In this video, we'll take a look at rational expressions and inequalities. Let's begin with rational expressions. Now, a rational expression is a fraction where at least one part of that fraction is a polynomial. So a rational expression is a fraction where either the top or the bottom is a polynomial. Now you might be thinking, what actually is a polynomial? Well, a polynomial is just a collection of constants and variables. For example, so we do polynomials. One example of a polynomial might be x squared plus 4, because we've got an x here, which is a variable, it's being squared, and then we've got a plus 4 there, which is just a constant. So it's a collection of variables and constants. Another polynomial might be y cubed plus y squared plus y, right? This is just a collection of variables which have been squared or even cubed. So we could say this is a polynomial to the degree of 3 because the highest power is 3. Okay, so a rational expression is a fraction where either the top or the bottom, or even both potentially, are polynomials. So let's do some examples of what a rational expression may look like. So e dot g, 4 divided by y minus 2 is a rational expression because we've got a fraction and the denominator, or the bottom half of the fraction, is a polynomial. Another example might be x cubed minus 4 divided by x plus 5. In this case, both the bottom and the top are polynomials, and they're being divided, so it's a fraction, so as a result it's a rational expression. Let's look at one last example, which might be 2x plus 2 divided by 1. Now, although we could technically simplify this to just 2x plus 2, since anything divided by 1 is the same thing, well, because we still have it in fraction form and the top half, or the top of that fraction, is a polynomial, this still technically counts as a rational expression. So that's something nice that we might want to keep in mind. Now, when we work with rational expressions, we often want to simplify them as far as we can. So we'll take a look at an example of a rational expression, and then we'll work together to solve that down. So, one example might be x squared minus 2x minus 8 over x squared minus 9x plus 20. So how do we simplify this down? Well, hopefully you remember from level 1 algebra that we can factorize this, factorize both polynomials down. So let's look at x squared minus 2x minus 8. So we need to find two multiples of 8. So let's look at, 4 and 2. If we have, well, it has to be a negative, right? So it looks like if we have negative 4 and positive 2, that would add to give me negative 2, and if we multiply them, it would give me negative 8. So our couple pair is negative 4 and 2. So this factorized down would be x minus 4 and x plus 2. That's a level 1 content, so you can check that video out if you're curious. And the second fraction, it would be x squared, the second quadratic would be x squared minus 9x plus 20. So let's find the couple multiples of 20. One example may be 10 and 2, but there's no way for us to get to negative 9, so it's not those two. We also have a 5 and 4. Now, 5 times 4 is 20, but we can't get to a negative number that way. However, if we have negative 5 and negative 4, well, negative 5 minus 4 is negative 9, and that also multiplies to positive 20. So this is our couple pair, so we can put these in brackets, x minus 5 and x minus 4. Now, if you remember, this was a fraction, so if I draw my line there, And now that we've factorized it, we can simplify. So remember, we always need to have our so our numerator and our denominator in the most simplified form possible before we start cancelling terms out. Okay, so we always need the most simplified form possible. So if we compare the denominator and the numerator, we can see both have x minus 4. So those can cancel out since we've factorized it. And this leaves us with x plus 2 and x minus 5. Now, that's our simplest form possible since we can't get any more simpler than that, right? So we've gone all the way, or the simplest way possible on our top, and all the simplest way possible on our bottom. So this is our final answer. Right, let's work through a second example. Let's say we had the rational expression x to the power of 7 added with 2x to the power of 6 plus x to the power of 5 divided by x cubed bracket x plus 1 to the power of 8. Now you can see the denominator here is actually been factored for us already. So what we want to do is we just need to factor out our top half. Now, so how do we factorize this? Well, obviously we don't know how to factorize anything with any tricks over the power of 2. So we know that we can do some cool techniques with quadratic terms, but what about with x to the power of 7? We don't know how to do that, right? So what we'll do is we'll take our highest or our smallest degree of x, and we'll bring that out, and then we'll just factorize using that technique. So essentially we'll look at our numerator and we'll see what has the lowest degree or the lowest power of x. We can see it's x to the power of 5, right? So what we'll do is we'll take x to the power of 5 out, and then we'll multiply it by whatever's left to essentially, if you know what I mean. So so we'll have x to the power of 5 multiplied by what gives me x to the power of 7. So x to the power of 5 multiplied by x squared gives me x to the power of 7. So we'll have x squared as our first term inside the bracket. That gets added with 2x. So 2x multiplied by x to the power of 5 gives me 2x to the power of 6. And finally, x to the power of 5 multiplied by 1 will give me x to the power of 5. So this is that numerator fully factorized. Now, if you remember, the denominator has already been factorized. So we've got x cubed bracket x plus 1 to the power of 8. Now, we've got a quadratic term in the numerator, right? So we can factorize that using the techniques that we know. So if we have x squared plus 2x plus 1, then we know 1 times 1 gives me 1, and 1 plus 1 gives me 2. So we can simplify this rational expression even further. So we've got x to the power of 5 multiplied by x plus 1 squared. So this is all over. So if I do that again, that is over x cubed multiplied by x plus 1 to the power of 8. So now we can simplify this down by comparing the powers. So this is equal to, well, if we compare our lone x terms here, x to the power of 5 divided by x to the power of 3. Now the x goes on the side with the higher degree, which is x to the power of 5. So we would have x to the power of 5 minus 3. So remember that when we divide two exponents, we actually subtract them from each other, right? So if we had, for example, x to the power of a divided by x to the power of b, assuming that the bases are the same, when we divide them, this will give us x to the power of a minus b. So in this case, we've got x to the power of 5 minus x to the power of 5 divided by x to the power of 3. This gives me x to the power of 5 minus 3. So we get x squared. So I might erase this here and just write x squared. Now we've got this here. We can think of this as doing the exact same thing. So we've got x plus 1 squared divided by x plus 1 to the power of 8. So the expression is going to stay on the side with the highest power, which is on the denominator. So we're going to have x squared on top divided by x plus 1. And that power is going to be 8 minus 2, which is going to be 6. The reason for that is that if we have So let's assume that we have x to the power of b divided by x to the power of a, where a is bigger than b. So assume a is larger than b. Then what we have here is this is going to be equal to x to the power of 1 over x to the power of a minus b. So this is the exact same thing that we're doing here. So we've got 1 over x plus 1. So think of x plus 1 as just a random variable. Let's call it a. So we've got 1 over a to the power of 8 minus 2, right? So 8 minus 2 gives us 6. So that's why we've got x plus 1 to the power of 6 there. And this is as fully simplified as we can get, right? So this is our final answer. We can also perform operations on rational expressions similar to adding, subtracting, multiplying, and dividing fractions. So let's look at another example. Let's say I had the expression 5 divided by m squared plus m plus 4. So this is all one fraction. And we add that with m minus 4 over m plus 4. So how do we simplify this down to as simple as possible? Well, hopefully you remember from simple fractions where the denominators are different, we essentially multiply crossways like this, right? So we multiply each numerator of each separate fraction by the denominator of the opposite fraction. So let's look at how we would do that. So we'll put an equal sign here, and essentially whatever the numerator is, I'm going to multiply it by the denominator of the other fraction. So we've got 5 multiplied by m plus 4, because that's on the opposite fraction, and that gets added with m minus 4 multiplied by the denominator of the first fraction, which would be m squared plus m plus 4. And this is all over the denominators multiplied together, right? So m squared plus m plus 4, and that's multiplied by m plus 4. And the reason that we do that is because we need our denominators to be the same for each fraction before we add them together, right? So if I just took like 5 over 4 added with 1 over 7, we need the most common denominator before we can add fractions together, right? This is how the definition of adding fractions, right? So the way I would do that is I would find the common multiple. So one way that we do it is we multiply the denominators together. So 4 times 7 would give me 28. Okay, so for the first fraction, we then multiply it by 7 on the top. So I'm multiplying by 7 over 7. So 7 over 7 is still 1, right? So 7 times 4 is 28, and 7 times 5 is 35. And that gets added with, 1 over 7 multiplied by 4 over 4. Now 4 over 4 is still 1, so we're still keeping it constant, but this time we're going to get 4 over 28. And that gives me 39 over 28, right? So that's a quick rundown of adding fractions if you've forgotten. And we're doing the exact same thing here. We've just got some algebraic terms, right? So I'm still multiplying 5 over m squared plus m plus 4. I'm still multiplying both sides by m plus 4. But m plus 4 divided by m plus 4 is still going to give me 1. So I'm keeping the equation constant. And the same is true for the other side, right? So, for example, m minus 4 over m plus 4 multiplied by m squared plus m plus 4 and m squared plus m plus 4. This is m squared plus m plus 4 divided by m squared plus m plus 4 still gives me 1. So I'm still multiplying by 1. So I'm keeping my equation constant. But now you can see that when I multiply the fractions together, we're going to get the same denominator both times. So that's the reason behind, or the logic behind doing so. So we've got this nice fraction up the top here. So is there anything that we can kind of factorize down a little bit more? In fact, why don't we expand our numerator first, right? So yeah, there doesn't seem to be any. Let's expand first and then see if there's anything that we can factorize down. So we're going to get 5m plus 20. added with m cubed plus m squared plus 4m minus 4m squared minus 4m minus 16. And then we're going to simplify that down. So that's going to give me 5m plus 4m gives me 9m minus 4m gives me 5m. Then we get 20 minus 16 plus 4. Then we got an m cubed term and an m squared term. Oh, sorry, m squared minus 4m squared gives me minus 3m squared. And if we simplify that down, well, it's already simplified, but if we write that in terms of highest degree of the polynomial first, we get we get m cubed minus 3m squared plus 5m plus 4. Okay, and that's divided by m squared plus m plus 4 divided by m plus 4. Multiplied by m plus 4. Now, I'm sure we could, well, you can see that we've got this plus 4 term here, right? And so what that means as a result is that we can't really factorize out this part here, right? So as a result, we're going to call this our most simple form as possible, and we're going to leave it at that, right? So what we've done is we've taken two rational expressions and we've added them together, and then we've made them into one fraction, right? So that's kind of we've made it as simple as we can, right? That makes sense at least. So we'll leave it at that. So that looks good to me. Let's look at one more where we divide two rational expressions together. Or maybe not rational expressions, but we divide two expressions together. So let's say we had m squared plus 5m plus 4. That gets divided by m squared minus 1 over m plus 5. So how do we do this? Well, this is the same as m squared plus 5m plus 4. So we've got one polynomial divided by m squared minus 1 over m plus 5. So this is our rational expression here. We can make this a rational expression by dividing by 1. Now, if you remember how to divide fractions, we flip the second fraction and then we just multiply across. So this is the same as m squared plus 5m plus 4 multiplied by m plus 5 over m squared minus 1. So let's have that over 1 there. And then we just multiply straight across. So we get m squared plus 5m plus 4. And that's multiplied by m plus 5. And then we just multiply our denominators together. So that gives us m squared minus 1 on the bottom. Now, let's simplify this polynomial here. So let's factorize it even further. So we're going to get 3 brackets. So if we have m squared plus 5m plus 4, and we have 1 and 4, so 1 times 4 gives us 4, and 1 plus 4 gives us 5. So this is the coupled multiple that we want. So this is the same as m plus 1, m plus 4, and m plus 5. Now, we can factorize the denominator as well. So m squared minus 1, this is difference of 2 squares. So this would give us m plus 1 and m minus 1. Or, yeah, I'll let you convince yourself that that is true. So now we've factorized the top and the bottom. We're going to see what cancels out. So we see that there's m plus 1 on both the numerator and the denominator. So let's cancel those out and let's see what we're left with. So we're left with m plus 4 multiplied by m plus 5 over m minus 1. Now, we can't go any further down, so this is our fully simplified answer. Finally, let's look at double inequalities. Now, a double inequality is a type of compound inequality. Here, we have two inequalities which are joined together. So, yeah, solving it is pretty much identical to normal inequalities, but this time, instead of applying the opposite operation to just two sides, we must apply the opposite operation to every part of the inequality. So let's look at an example. So let's say we have -2 is less than x plus 3, which is less than 7. So how do we solve for x? Well, we need to get rid of this plus 3, so the opposite operation is subtracting 3 from both sides. So if I subtract 3 from both sides, I'm going to get -3, -3, and -3. So -2 minus 3 gives me -5, which is less than x plus 3 minus 3, which is just x, and that's less than 7 minus 3, which is 4. So now we've got x isolated, and if we look at our answer here, we're saying x is greater than -5, but less than 4. So this is how we do it. Let's look at a slightly different or more complex example. So assume we have the inequality 5 is less than -3x plus 7, which is less than 23. So how do we go about solving this? Well, first we're going to get, if you remember, that our anti-bedmass or SAMDEB is our order of operations when rearranging. So we need to get rid of that plus 7. So we need to subtract 7, which is the opposite operation, on every side. So we get 5 minus 7 is less than -3x plus 7 minus 7 which is less than 23 minus 7. Now 5 minus 7 gives us a -2. That's less than -3x, which is less than 23 minus 7, which is 16. So now we've got -2 is less than -3x, which is less than 16. So the last thing we need to do is get rid of the coefficient in front of x, which is -3. So in order to do this, I'm going to divide by -3 on every side. So -3 divided by -3 divided by -3. However, if you remember, when we have inequalities, we need to flip the sign and when we divide or multiply by a negative number. So as a result, we're going to get 2/3. And because we've divided by a negative number, we need to flip our inequality. So the inequality becomes facing the 2/3. That's -3 divided by -3 gives us just x. And then we've got 16 divided by -3. Now, because we've divided by a negative number, we then still need to flip our inequality. So our inequality is going to go to facing the left side, and then we're going to just have -16/3. So we've now isolated x. So if I rewrite this how we've been writing it before, we have x is less than, -16/3 is less than x, but x is less than 2/3. And this is our final answer. So a little bit tricky there. We just have to keep an eye out on if we have a negative dividing or multiplying by a negative number, then we need to make sure we're flipping our inequality signs. Sweet, that's it for this video. Thanks for watching. I'll see you guys in the next video. Cheers.